Thanks to Matt for the big scale. As people who know me, I tend to work on the small scale, so you'll see this is a much smaller scale than what Matt looked at. And I'm looking at the process, physico-chemical processes within permafrost terrains. People haven't really said it, but the pandemic's made a bit of a dent in most people's in this program. And this was being a sort of new idea. We didn't really get into the field until 2022. And so I'll give you what we've got, but there's still a long way to go. I'm going to skip through most of that. Again, climate change, people have talked about that, and permafrost degradation is going to be an ever-present reality. We're going to have to deal with that. How do we deal with that? Groundwater flow and groundwater surface water interactions within permafrost active layer systems, I think, are poorly understood. They're still poorly understood. And the chemistry of them is even worse understood. And these issues have implications for infrastructure stability, water quality, quantity, and particularly sustainable development in northern terrains. So this is a research site, and what attracted me to this research site was this. You have some extremely high concentration waters in this. It's actually part of the Inuviatuk Highway, IPH as it's called, and it was built between 2013 and 2017. And this is a borrow pit that was dug, so this is about 100 meters or something like that. It's not very big, it's pretty small. And I want to know why and how you generate large solute concentrations in permafrost cold climate conditions. You really shouldn't in most chemical situations. And so we have a fairly good idea. This is actually now that these high concentrations are coming from the permafrost itself. So they're actually incorporated in the permafrost, and the thawing permafrost, because we've stripped off the overlying insulation, is now generating these high solute concentration waters. And some of these are pretty nasty. So they've got some high uranium. There's multiple chemicals multiple elements that are above guidelines. So I wanted to also think about this in terms of what is happening in the annual cycle. If you were doing an annual cycle system in the south here, we have sensors and instruments that allow us to go and put those in there, and we can get automated data. Those haven't really been tried in the north because basically it's too cold, everything freezes, and batteries, etc., don't like it. But we worked with a company in Vancouver, and we came up with some ideas. And so this is the instrument, hydrogeological instrumentation we installed in 2022 to start looking at the seasonal cycle. And I particularly want to know what happened in winter. Everybody sort of has this idea that winter is sort of not much happens. I sort of tend to think it does happen. A lot happens in winter. These are the systems I went through this last year. These are the different sensors. This is the total earth pressure and a pore water pressure and ground temperature sensor. This is just pore water pressure and ground temperature. This is water content, temperature, and conductivity sensor. The active layer in this area is 0.4 to 1.8 meters thick. The aquifer that you saw all those that we instrumented in the pit are just gravel lenses and we sampled those gravel lenses for the water and the surface water. So here's the water content, conductivity, temperature sensor data. First thing you see, well, we thought we figured it, but the data logger died in March. The battery just basically ran out. But what you can see, a couple of things you can really see is that these are fairly depth-dependent profiles. The gravel aquifer at 100 centimeters really doesn't get very cold, whereas the 45 centimeter pebbly mud gets very cold and freezes a lot earlier. The shallow sites also tend to be noisy. You see these quite big pronounced changes where you don't see that in the deeper site. Sort of things you might expect. The thaw, on contrast to the freeze up, is actually very coherent. So everything sort of seems to thaw pretty much the same. Quite different behavior, which I think is actually an interesting thing. And so then you get into some situation where the active layer is actually unfrozen and each side is doing its own thing. If we take contrast between a pebbly mud and at 45 centimeters and a 1 meter deep aquifer gravel, you see quite different profiles. The freezing shuts off the center current and down in the 40.45 meter. This was a fully frozen sensor. There's no current. It's a voltmetric system, so it can't actually produce a voltage, and therefore it's producing nothing. Whereas in the deeper aquifer, you see that until the battery died, it's pretty much unimpacted. And even when you get the battery back, you're still in late winter, you've still got actually some current in comparison to here. Then you're in deeper level, but you look at the thaw, very, very rapid in the aquifer gravel, quite slow in the mud. There's clear. More importantly, if insulation was the driver, the deeper aquifer should thaw later, but in fact it thaws earlier, 28th of June versus the 1st of July. There's clearly advective heating going on in the aquifer. All through winter, as we shall see, there's actual aquifer activity. This is the pore pressure data, and so this is the pore pressure and the temperature of 120 to 10 centimeter depth sensor in gravels. Here we didn't get any, the battery did last in these sensors, so we get a full record, lovely. And what you see is the complete decoupling between the temperature and the pore pressure, which is sort of what you might expect for an aquifer. It's what you should see. But you get a high compression. It implies unfrozen conditions, and that was confirmed when we drilled this in early May, and that there was actually water in this aquifer. Even though it's only half a meter, 3/4 of a meter down, it hadn't frozen. Interestingly, in the gravels and the aquifers, you always see temperature stays above -2 degrees C. And I'll come back to that. Keep that in mind. Just like in the previous one, there's indications that there's more going on here during winter than we think. Again, pore pressure, constant aquifer saturation, groundwater flow likely occurred over much of the winter. This is a negative pore pressure. So this sensor is at 110 centimeter depth, same as before, but it's in mud now. And you can see the temperature goes way down to -3.5 or thereabouts. You have mostly decoupled, but you actually have slight periods of coupling between the temperature and the sensor. What is really interesting is that the pore pressure initially starts to go up in January, and then rapidly drops once you go below -2 degrees C. That -2 degrees C comes up time and time again. And then over much of winter, you get negative pore pressures. That's suction. And as has been often talked about in the permafrost community, during winter you should get what's called cryosuction, which is essentially suction due to capillary movement of water up through the profile. This is the first recording of cryosuction in the field that we know of. And values are much lower than theoretical pore scale values, which are 500, 600 kilopascals. But actually, when you actually get to hand scale, empirical rock scale laboratory tests basically come up with the same 20 to 100 kilopascal cryosuction values. So I actually think this is a really good result. Never been able to be done before. This one's a bit more, I'm not sure I believe it myself, but we'll see. So this is the individual temperature record in the green and the ground temperature for a 45 centimeter depth sensor. At the beginning of winter, there's an 8-day lag between these peaks. And by the end of winter, there's a 2-day lag. This sensor undoubtedly, it got down to -7.5, undoubtedly froze. That 2-day lag, there is a 4 times heat conductance change when you go from water to ice. And what you see is a change from 8-day to 2-day, a 4-day difference in temperature variation. So again, looks pretty good. And overlay the pore pressure on that, and there's a 1-to-1 correspondence between the ground temperature and the pore pressure. And what you see here is, again, at -2 degrees C, and between 0 and -2, you get a 15 kilopascal per degree C change in cryosuction. Whereas once you get between -2 and once the sensor gets below between -2 and -5, you get a 2 to 4 kilopascal degree C change. What this is telling you is that I think, we don't have enough data, but this is my theory, is that temperature thresholds are important. At 0, you actually freeze free pore water within your sediment. Below 0, there is still probably 10 to 15% free water. And that 10 to 15% free water is in films, in advective, in soil components. And so essentially these different thresholds are these different reservoirs. That makes a huge implication for soil engineering in permafrost conditions, because that changes the rheology of their winter conditions. So I think we have a mechanism here for really getting to grips with what actually happens in these soils with these sensors. I'll let you read this, but essentially that these sensors they're standard things, tools for southern non-permafrost conditions. I think we can actually use them in northern conditions now, and they can tell us an awful lot about what's going on during winter, during summer, across the northern permafrost landscapes. Essentially, permafrost active layer hydrogeology can be much better defined and will lead to better engineering solutions. I haven't really talked about the chemistry, but there's a whole other chemistry story that we're still working on. How did those high soluble permafrost conditions arrive? That's a chemical weathering story that is really still being pieced together.